Alright guys, so hopefully by now the aldol condensation is starting to make a little bit more sense. But what happens when you have an asymmetrical ketone? That presents a problem. So whenever you're reacting an enolate-mediated reaction on an asymmetrical ketone, two enolates may be possible. So we're going to have to use a directed reaction, okay? Directed reactions are what we use to pick the enolate that we want. Because if you only have one choice of enolate, then your enolate is going to hit your electrophile and you're done. But what if you have two possible enolates? Then which one is the one that attacks the electrophilic carbon? Who knows? Well, that's why we have to use thermodynamic versus kinetic control. So guys, the thermodynamic enolate, we've learned this before, is the more substituted one, okay? It's going to be favored by small bases, okay? Whereas the kinetic enolate is the less substituted one. It's the one that's easier to reach, and it's favored by bulky bases, okay? So what that means is that if I want to run an aldol reaction, let's say on the right side of my ketone here, I only want to attack with the enolate on the right side, then I would use a small base, for example, NaOH, okay? Or any other small base. However, if I wanted to react on the less substituted side of the ring, making my enolate on the left side and then having that attack an electrophile, then I definitely have to use a bulky base. And for that, we've got two options, but the most popular for this chapter being LDA, because of the fact that it's a non-nucleophilic base, so we don't have to worry that it's going to actually add to anything. It's just going to remove a hydrogen, okay? But also, terbutoxide would be a possibility. Excellent, guys. So now, go ahead and try to predict the product for the following reaction, and then I'll jump in.